We were discussing clustering techniques, and uh, in last class we have discussed what is k-means clustering. So just a quick recap. Uh, there are some endpoints, right? And we have taken an indicator variable r and k, which is like just to visualize, we can see that it has like it can take value 0 or 1 for every x point. Then we said that there is a distortion function which we can compose that way. And there are two parameters here, r and k, like the belongingness of x to which to the kth cluster, and mu k, what is my centroid. So one by one, we can minimize our cost function on both of the parameters, right? So first, let's say, uh, in the order we take parameter r and k and fix mu k. And when we minimized this cost function, we found out that x should be assigned to the cluster where it is near to the mu k, right? So this quantity should be small, right? And hence r and k should be 1 for that particular uh, cluster, and rest of them should be 0, right? Then we said that now once you fix R and K, it means what happened in first iteration when you optimized over R and K, it means you have found out which X belongs to which cluster. And cluster is represented by the centroid element mu1, mu2, mu3, right? So in first phase, I would say, you have decided on like the belongingness of X to the cluster, K cluster, right? So let's say if there are 3 clusters and they are represented by mu1, mu2, mu3. So this X is near to mu1. So hence you say that this X belongs to cluster 1, right? Similarly, you do it for every point, and for this, you do it for every point. Hence you minimize your cost function with respect to R and K, right? It means you have already decided that my X point belongs to this particular cluster based on the proximity. Then you said that, okay, now let's minimize your J on this parameter mu k. So now the scenario is this. Let's say you started with these 3 points, mu1, mu2, mu3, right? And this is your cluster 1. This is your cluster 2, right? This is your cluster 2. And this is your cluster 3. So because these points, all these points were near to mu1, so you have taken this cluster 1. These points are near to mu2. That's why you said that these all points belong to cluster 2. And these points all near to mu3, and hence you said this is a cluster 3. Now you want to minimize over mu k. So you say that if you put mu k here, then it is a problem, because the cost function says that distance of xn from mu k, right? So if you take a distance of every x from this mu k, it is very large distance, right? It is a very large distance. Instead, you put your centroid here, right? Here is the center. I don't say centroid, it's a prototype element, right? Instead, you put this element mu k here, and then you calculate the distance. You will find it out. Then if it is at the center, this prototype element, if it is at the center, then the distance, that the cost of function j will be minimized. It can be proved, right? So we said that you can minimize it. You can take this function, right? Fix your R and K. It means you have already decided which point belongs to which cluster, right? Now you already decided which points belong to which cluster. It means R and K is fixed now. Now this mu K is not fixed. You are minimizing this cost function over mu K, right? So if you take the derivative with respect to mu K and put it equals to 0, you get this form, right? We have discussed that thing. We said that if you minimize over mu K, you will get this kind of formulation which says that you just add all the points belong to a particular cluster, right? Only that particular cluster for kth, right? For kth cluster, you add all the points which belong to kth cluster, and then you divide it by the number of points in that cluster, right? It will give you a center. It will give you an average element. It is a kind of taking an average element, which is nothing but it's a mean and which comes at the center, right? So this is like for every k element, you will do it one by one. For every kth cluster, you do it one by one, and hence you will get the centroid. Now again, this is the first iteration. So you have minimized over Rn, and then you minimized over your mu. Your first iteration is over. Then you again fix like which now you go for every point one by one and say that which it whether your point belongs to cluster 1 or 2. It may change, right? Once it we will show it, I will try to show you using some pictorial diagram. So this is what we have seen so far. So there are two phases, right? So first we need to assign the data points to a cluster, and then we need to compute the mean of that cluster. This is two phases, right? Here we want to find out, we are optimizing over R, and here we are optimizing over mu. And we do it repeatedly. We do this in iteration. So in iteration 1, we do that. In iteration 2, 3, 4, 5. And for every iteration, my cost function will keep on minimizing, right? So let's take an example here. This is a data set, right? Old faithful data set. It's have 2 cluster. So now if you take a 2 cluster, k, you take a value k equals to 2, right? And when you take k value equals to 2, you put one centroid somewhere here, and the other, sorry, I'm really sorry, I'm saying centroid. So it is again, you take this as prototype element mu k here for one class and the other class, right? Now you assign the nearest point to this prototype. So, or if you bisect this line somewhere here, all these points belong to this cluster, right? And the above this line, all these points belong to that cluster. That's why they are shaded in blue and red. So this is assignment of R. So we have done assignment of R. So we have found out like my point belongs to this particular cluster. Then we need to calculate the centroid or mean, right? Mean. Then if we calculate the mean, so you just average these all red points, and because the density is heavy this side, and so your mean will shift somewhere here, right? Your mean will shift somewhere here. And similarly for blue, when you take a mean, most of the points fall this side. So that's why your mean will fall to this, come here, right? This is your one iteration. This one iteration is done, right? Then you go to for second iteration, because this is your new mean now. So this is your new prototype mu1, and this is your second prototype mu2. Again, you calculate the assignment of your point. So now these points, all these points, you just see these blue points here, they are more near to this centroid, upper centroid, and hence they will take a color red, right? So this is our assignment. Again, we need to recalculate the mean element. When we calculate the mean, it will shift somewhere in the more into the center. It will shift somewhere more into the center, and hence this is my first iteration done, the second iteration done here, right? For R and mu. Again, we calculate what is my new assignment R, and once I assigned every element to this prototype element mu1 and mu2, again I need to calculate the mean, right? This is my third iteration, and hence this is my fourth iteration. So it will happen that I may then there will be no change. You will observe no change after some times. and once you observe no change, then you can stop, right? So this is your cost function J, right? So in your first iteration, you drastically come here. Then in second iteration, you further minimize, and then this first. Okay, so this graph is shown here. This is your assignment for R, right? Then this is for mu. So when you minimize over R and then mu, then here you come, then you just minimize over R and mu. Second iteration, then R and mu. Third iteration, then R and mu. Fourth iteration, right? So in fourth iteration, you will feel that there will be no change in the cost function. So hence you can stop here. This is k-means clustering. You might have seen it so many times. And uh, are there any questions so far here, till here? So, okay, so there is one question. Sir, initially mu is randomly chosen, right? Yes, initially mu is randomly chosen. And the good part is mu may not be any point among the data set, right? Here you can see clearly from this picture. So generally you might have seen so many times during the implementation, you might have taken your mu one of the points randomly, right? But it is not necessary. This k-means clustering says that you can take any point and just say that it is a mu, right? It may not belong to a data set, right? It may not belong to a data set, right? As it has seen. So randomly you can choose. Even you can choose two random points here as well, right? Mu1 and mu2. Nobody can stop you by doing that, right? Okay, so the second question is, so does that mean there is a chance of getting optimal solution in the first iteration? Yeah, if you are very lucky and you might have chosen randomly some points like here, you in the first stage itself, you just stage mu1 and mu2 like this, then you are done, right? You cannot optimize further. Any any uh, any other question? So the other observation is that you may not end up every time the same clusters, right? So this happens because of my local minima, and I will try to show you like where that minima comes into a picture, because of we are maximizing the likelihood, right? And when we are trying to maximize my likelihood during this operation. So it may happen that if you start with some the another, so you two people in a class may start with some two different random choices, and you may end up in different two clusters, right? It may happen. So that is not very new for this k-means cluster, right? It may happen that you may end up in having two different clusters in two different learning or modeling, right? You do it on your own and you just see yourself. Any other question before I proceed further? Okay, fine. So if there are no questions, let's start. Let's go to there are limitations. Every data point is assigned uniquely to one of the cluster, right? So either, for an example, there are two centroid elements like this, mu1 and mu2, and this is my point. It is just a halfway. So the distance from this point and this point is equal. Despite of that same distance, you have to choose whether it belongs to this cluster or either it belongs to this cluster. So you cannot say that this belongs to the both of them with equal probability. No, there is no probabilistic interpretation here. So you have to choose its like belongingness to one of the cluster. Fine. So just to overcome this thing, and also the clusters are always spherical, right? So spherical, in a sense, you may say that this is not spherical, right? But if you just fill it, the belongingness, if you put a grid here, right? If you put a grid somewhere here, So because the equal distance, you are saying norm distance, so it will produce a circle here. It will produce a circle. And if you fill it, you will see that for every point, all this belongs to red, and the below to this point belongs to the blue point. Because you may see it as a very big ice sphere right here, and it will just bisect orthogonally somewhere. So the shape of the clusters will always be spherical here, right? So then there are two disadvantages. One is like you can't have a choice like where you can take ellipsoids clusters, right? This could be the case. And because if you're doing k-means clustering, then you have a isotropic Gaussians, right? Isotropic Gaussians, and you will have this way of clusters, which is not fruitful, right? Because clusters can have any shape here, like clusters can be of this shape, right? And you can't do better than that, better using this k-means clustering. The other is like this deterministic nature of belongingness. You can't say it in, you can't do soft assignments, right? Sometimes people say it fuzzy clustering. Fuzzy means like you can have a belongingness 0.3 and 0.7 of a same point, right? You can say that this point belongs to this cluster with 0.7 probability, and this same point belongs to this cluster with 0.3 probability, right? You can't do that in k-means clustering. So majorly there are two disadvantages. They are isotropic in nature, which I have not, I think, which is not written here, and the other is like this soft assignments. So to overcome that, we need to do a probabilistic modeling, and that probabilistic modeling, we take a mixture of Gaussians, right? We take a mixture of Gaussians. So I will move very slowly and step by step. I feel this is a bit probabilistic and easy to understand. You need to focus on it. And if you have any problem, let me know. So I will not rush on these slides. Today I will go very slowly. And when I feel that you feel comfortable, then I can go ahead, right? Okay, so let's see let's see, this is there are this is the kind of a scatteredness of our data points in a space, two-dimensional space, right? If this is a scatteredness of a point in two-dimensional space and you want to model it using single Gaussian, what will happen? Then single Gaussian can have a covariance matrix and one mean, right? So if this is a mean here, so it can come where somewhere here in the mean, and the covariance matrix will come where somewhere like this, right? So it is like this single, for if you are modeling it using a single Gaussian and you want to maximize the likelihood over single Gaussian, so you are finding out two parameters, covariance matrix and a mean, and then covariance matrix and mean will give you this kind of a Gaussian, right? Which may not be a proper fit because it is showing that this is a density, good density here, right? There is a good density here. But as you see that because the data set available here doesn't say any presence in this region, hence this is not using a unimodel Gaussian is not a good approach. So what is the other option? They say that don't take single Gaussian, right? You take more than one Gaussian and model it first. You take small one Gaussian here, you take second Gaussian here, right? And you take third Gaussian here, right? Then it is a mixture of Gaussians, right? Rather than taking a single Gaussian, you are taking three Gaussians. So then it is a proper fit. Now you can see that it is using these three Gaussians, we can have a proper fit of this data set. Even you can use more than three Gaussians, right? Even you can use 10 Gaussians, right? And then it may be like a trade-off, how much you want to accommodate these Gaussians. So this is always a hyperparameter. What is the right number of clusters you want to see into your data set? We will see, like I will try to cover that part in Bayesian thing. So you might have not seen so far like how to come up with the optimal value of k so far. K means the number of clusters. So I will try to cover that part also, right? using Bayesian learning. So this is, for an example, let's say somebody comes magically and tell us that there are three clusters in a data set. So then once you know that number three, then you can easily find out that if there are three clusters, the first mean is here, the second mean is here, then third mean is here, and the covariance matrix respectively is this one, right? So you can find it out the moment you get to know that there are three Gaussians here available. And if once you model, you want to see in 3 dimension, what is the density look like? This is how you can see the density, right? So it is a z-axis, which will tell you what is the probability of belonging at this point. So this point is having a high, this much probability, and this point is having a very high probability, right? This much. So this is nothing but it's a 2 dimension level curves, and the same probability if you see in 3 dimension, it is this one, right? So any question on this? Like why we say mixture of Gaussians? First thing is first. I hope this term is clear to you. Why it is known as mixture of Gaussians? Because we are taking more than one Gaussian, and using these to more than one Gaussians, we try to form the density of a data set, right? This is because, and we can mix these Gaussians, so that's why they are known as mixture of Gaussians. Is that okay with you? Yes or no? Fine, good, very good. It's a very important topic, I would say, very very important topic. And once you go into that deep learning using GAN and try to modulate the densities, try to model the densities. This is just a first baby step of that, right? So you just give your whole attention on learning this. How you are estimating a density of a data set, right? So this is a one way of estimating a density of a data set, right? Though you can see it as a Gaussian, and you can see it as this same modeling as clustering also, but the same modeling you can see as how you can model the density of a data set, right? Density of a data set. Why I'm saying density of a data set? If you don't say that this point is for cluster 1, this point is for cluster 2, this point is for cluster 3, and I just say that what is the probability. So just try to understand these two different problems, but having the same solution. So if somebody comes and tell me, what do you think, what is the probability of generating this point here? So you just map this point here and you see that the probability of generating this point is almost zero, right? But if you say, what is the probability of generating this point? So you just go to this thing, you see that this point is somewhere here. The probability of generating is very, very high, right? So I am not caring here what is this point belongs to which cluster. So there is no concept of clustering here. I am just interested in estimating the density of a given point. So if you just estimate the density of all the points in a space, it will look like this, right? There is one Gaussian somewhere here, the second Gaussian is here, and the third Gaussian is here. The same modeling, you can use it for clustering also. Now you bring a concept like whether it is belongs to cluster 1, cluster 2, and cluster 3. Then for this same point, if you ask me, what do you think? This is a second problem. What do you think? What this point comes from cluster 1, cluster 2, or cluster 3? So now if this point is sitting here, so the let's say it is very near to this point, blue one, right? So then you say, because it is very near to this blue cluster, so the probability of belongingness to this axis very high to this blue, right? But as I said, it is a probabilistic interpretation. Then you can say it belongs to this blue cluster with 0.6 probability, this green one with 0.2 probable, 0.1 probability, and for this red, it belongs to 0.3 probability, right? So it is having a distribution which says that the belongingness to each of the cluster will be 0.6, 0.3, 0.1. The methodology is same, right? And we can formulate two different problems using the same method, right? So I will try, first I will cover this clustering aspect, right? And then later either using one or two slides, I will try to cover that density estimation thing, right? So first I will cover this part, mixture of Gaussian, it means clustering aspect. Okay. With any questions so far? Yes. Okay. If you don't have any question, let's try to deep down into the detail, mathematical details, right? So let's say I know I'm interested in calculating the density of this point X, right? So I know that it can be generated from this cluster with probability P1, right? With probability P1. I don't care like how small that probability is or how big that probability is, but there is always a probability of generating this point from this cluster. Similarly, from this green cluster, I have a probability of generating this point, and let's say that probability is P2. And then generating the same point from the third cluster is P3. If you ask me, right, obviously the sum of these probability, right, if I am assuming only there are three clusters, the sum of these three probabilities will be 1, right? So how to write it in mathematical expression? So the probability P1, I can write it like this. What is the probability of seeing my cluster 1, right? What is the probability of seeing cluster 1? And once I see the cluster 1, what is the probability of generating that X from that cluster 1, right? This is probability is known is P1, right? This probability is P1. Then I say, what is the probability of seeing cluster 2, right? Green one. What is the probability of seeing this cluster 2? And what is the probability of seeing X from that cluster 2? What is the probability of seeing X from this cluster 2, right? From this cluster 2. What is the probability of seeing this cluster 3? And what is the probability of seeing X from this cluster 3, right? This is P3. If I sum these three probabilities, I will get the probability of seeing the X. Because I don't care, I am marginalizing the clusters here. So I don't care, I am marginalizing over clusters, right? Ci. So I don't care from which cluster my X is coming. I am really interested in seeing X only. I don't care from where this cluster is coming, right? So because we have seen that it's a mixture of Gaussians, I know these conditional probabilities are Gaussian, right? Because I know that all this is a mixture of Gaussian. So probability of seeing from the cluster blue one, it means I need to see how much far it is from the mean and what is the covariance matrix. So all these conditional probabilities, probability of X given C1, probability of X given C2, probabilities, they are Gaussian probabilities, right? They are Gaussian probabilities, right? This one. And probability of seeing C1, C2, C3 is the prior probability of seeing the cluster, which we say pi1, pi2, and pi3, right? And if you sum over this, right, for all clusters, you will get the probability of seeing X, right? And the sum of these prior probability will always be 1 because we say that in the universe there are only 3 clusters are possible. And if I confine my universe and there are only 3 clusters possible, so definitely the sum of the probability of seeing the clusters will be 1, right? And because it is a probability, it is always fall between 0 to 1, right? With equality, right? It may be possible that I cannot have any probabilities of seeing cluster 2, right? In that case, pi 2 will be 0. Right. So this is a important construct to and you should understand this, right? How to write this thing, how to read this thing. If you have any problem in reading and writing and understanding this thing, please let me know so that I can clarify. It will grow bigger and bigger in complexity later on the slides. So if you feel bit like unclear here, you can let me know so that I can clarify that thing. So can you let me know more, all of you or most of you, like what is your status? Do you understand this thing? Yes means you understood and no means okay, no doubt. No doubt is fine. Understood. Fine, good. Okay, very good. Very nice. Very good. So this is like, so this is the first step of like how we can write it and then this thing. So now there's another word that we need to understand is a latent variables, right? Latent variables. So here I see that here if I just see that the probability of X, right? So there are one latent thing is available. If you have seen a X, right? If you have seen a X in your data set, it may be possible there were three clusters. So there were three probability P1, P2, and P3 coming from these clusters, right? But once the point is available, it is present in your data set. It may come from from one of the three, right? Because it has already appeared, right? So once you have seen a point, it may come either from one or two or from three, right? Because the way we have constructed the probability, it is like we are marginalizing it. But now we are generating a data set. The moment we are generating a data set, it is like this. First, you find it out what cluster I can see. So there is a distribution over pi1, pi2, pi3. So you choose randomly one of the cluster. So you say, let's say I choose cluster C2. Then the moment you choose cluster C2, then what is the probability of generating X from this cluster C2, right? So what is the probability of generating X from that cluster C2? Now, if this X is available in your data set and I'm asking you, what do you think? This X comes from cluster 1 or cluster 2 or cluster 3, right? So you can guess on it, right? There is nothing in this world which can deterministically tell you that this X is coming from cluster 2, right? Because the moment it was generated, you were not there at that time. You are seeing only X right now. So if somebody is showing you X, then he may ask you, what do you think? This X is coming from which cluster? Then you need to infer on it. So just to make it intuitively, for an example, this is cluster 1, this is cluster 2, this is cluster 3, and I am giving you this X here. So what do you think? Either it is coming from 1 or 2 or 3. What do you think? This X is coming from which cluster? So this is your guess, right? So the moment you say a 3, this is your guess. But still, there is nothing in this world which can stop this X coming from 1, right? Because though the probability is very, very less, it may be 0.0001, but still it can come from that cluster. So now we have to make a guess, and that guess should be confident enough, right? So now to make that confidence in guessing, we guess on the probability distribution, right? So we infer that if this X would have appeared in a data set, then the probability of coming from these three clusters will, let's say, is P1, P2, P3, and you may go for the highest probability then. Then you say that because I need to guess, I will go for the higher confidence, and because higher confidence means higher probability, I will say that among all the three probabilities which is higher, I will say that this X belongs to that particular cluster. This is what is the general phenomena here, or of a methodology, right? So just to modulate this situation, I never know whether this X comes from which cluster. So I say that there is a latent variable, and that latent variable will represent the cluster. So that latent variable, let's say, is Z. And if I say that it is belong from cluster 1, so I say that the latent variable for this particular nth point, it is 100, because now I am fixing that this X is belong to cluster 1, or this Zn may be 0, 10. Then I am saying I feel that it is coming from clusters 2. So the latent assignment will be 1010. And if somebody think that this X belongs to comes from cluster 3, then my latent assignment will be 001. So this latent variable somewhere capturing the idea of belongingness of that X to that particular cluster, right? And in modeling, then we will infer what is the probability of Z given X, right? Given X. So because Z is having 3 assignment, it is 10001001001, then you will have a probability. And let's say this probability is 0.2, 0.2 for 100, 0.2 for 010, and zero point 0.6 for 001. Then you say that X belongs to the third cluster. This is what is the broad idea will be, right? So just to model this situation, we are using latent variables here. And these latent variables are discrete latent variable, right? We will see the case where the latent variable can be continuous also. But here I am saying whether my X belongs to cluster 1 or cluster 2 or cluster 3. So this is a discrete case, right? So we are modeling discrete latent variables here. Okay. This is, I have already told you what it is, right? This is also I told you. This is a latent variable Z, which correspond to for every nth point, right? So it is a vector. This vector dimension will be k by 1, because they are k cluster, and because you are assigning your point to one of the cluster, you are assigning your xn point to one of the cluster. Hence, it can be one hot vector encoding, and if you sum all the components of this Z, it should always be equal to 1, right? This is, so just to demonstrate, this Z can have two values. If it belongs to cluster 1, it can have 10, and if your kth point belongs to second cluster, it having 01, right? And this is same. If it is, there are 3 cluster, it is 100, 010, 001. So we have already said that. So the goal of a mixture models will be, this will be given to you, the data set will be given to you, and then you may ask to infer how many clusters are there and which point belongs to which cluster, right? So let's say you are good in guessing and doing the things. Sorry, you are good in modeling the things, then the output will be this. This is the ideal output which you may expect. And this is the true output, right? Because as I said, when during the generation, this red point is belonging from the first cluster, right? But during the inference, you don't know this point belongs to either this cluster or this second cluster or third cluster. So hence, there may be a distribution over a probability on this point, and color is showing which is having a higher probability. For an example, here, this is having a blue color more shaded, and this is having some green and red color mixed, right? So we can't infer accurately that X is coming from which uh, cluster during the generation. but we try our best and we try to find out what the probability distribution for every x, and distribution is over the latent variables z. Okay, any questions so far? You should be very clear in understanding the problem statement. Okay, very nice. Good. Very good. Okay, then let's go ahead. So the rule of the game is same. We are having joint distribution. Let's say if this is a joint distribution over x comma z, then I will find out what is the probability of a z, and then try to find out what is the probability of x given z, and then I will multiply it. If I multiply it, it is nothing but a joint distribution of x comma z, right? And z is the probability of seeing the cluster, and somewhere it is if you just take this joint probability distribution, right? So if you sum over x, this joint distribution x comma z, you will get the probability of a g, right? So it's a marginalized distribution, and it is a conditional distribution. Given a z, if I say that this x is coming from cluster 2, right? This is coming from cluster 2. So this is 1, this is 2, this is 3. So if I fix my z, if I say that it is 2, what do you think, what is the probability of x? Then it is very simple, right? You know the mean of this cluster, you know the covariance matrix of this cluster, and for finding out what is the probability of generating this x is simple then, right? From the density. So it is a conditional thing. Okay. In last minute, I want to wind up this, right? And then I will stop. So there is a way to write few things here. So this is the probability of z, right? So if you fix, just I am trying to teach you how to read this thing. So if this is the probability of a z, right? So z is a variable. Let's say I am saying z equals to 100, right? So you can write in general probability of z, it means you are seeing all three probabilities all together. Probability of z equals to 100, probability of z equals to 010, probability of z equals to 001, right? So I'm just writing it for one case. So probability of z equals to 100, you can write it this way, right? So it means you can write it pi 1 multiply pi 2 multiply pi 3, right? Pi 2 is nothing but the prior probability of seeing the cluster. Pi 3. And then you are exponenting it with the zk. So here zk means z1, z2 and z3. So just for this case, z1 is 1, z2 is 0 and z3 is 0. Hence the probability will be pi 1 only. The probability of pi 1 to the power 1 is pi 1 only, right? So in general, you are saying that the probability of z, it means probability of particular cluster is either pi 1, pi 2, pi 3, and it depends upon the assignment of that z. If you are seeing the probability of first cluster, then it is pi 1. If you are seeing probability of second cluster, it is pi 2, and the probability of third cluster is pi 3. I hope this is quite clear to you why they are writing it in this product form. It is a very simple way of, if you don't understand, it may seem very complex, but it is a very simple way of writing the things, concise way of writing the things. Can you just nod your head on this? Do you understand why what is the meaning of this? Okay. Okay, good. Very good. Very good. Good. Fine. So I'll stop here, and maybe tomorrow is a holiday, so I will take class on Wednesday. Thank you, Vince. Drop your attendance.